Hello and welcome to Chandler Science AP Physics 1 Projectile, Motion, and Freefall problem. So in this video, I am going to do several problems with graphs and then with word problems over projectile motion and just kind of work out the kinks, and hopefully you follow along, pause the video, solve the problem on your own, see how I do it, whatever you got to do to figure out how these problems work, because we got to know how to do them. So if you're one of my students, don't forget you are taking your notes and you are going to ask one question on the Schoology discussion forum, and you're going to answer someone else's question on the Schoology discussion forum. If you're not my student and you're from somewhere else on the internet, welcome and hope you enjoy. Let's begin. Alright gang, as usual, we're going to start with graphs, because graphs are awesome and amazing and you got to learn how to do graphs. So before we had a problem about a ball launched in the air and it kind of had motion like this, right? So it's got initial horizontal velocity and it has initial vertical velocity. Now I just want to be clear, and I'm going to draw different graphs for both these things, okay? I want you to practice drawing vertical position. Now this looks weird because I got like X and Y, but remember X stands for position and the subscript Y is for the vertical direction position graph versus time graph for this, and then a horizontal position graph for this thing. And then I want you to practice drawing velocity, vertical velocity time graphs, and horizontal velocity time graphs. All right. Now the funny thing is, I'm going to do the first one for you. So remember this: what this object was doing was launched it at an angle, at a 30-degree angle up in the air. It went through the air, got to its highest point right here, and then came back down to the ground. Okay, hit the ground right here. So interestingly enough, its vertical position looks almost exactly like the drawing of the object's motion through the air. So it literally goes up like this, down, and then back down to the ground. Because if you think about it, it's launching from the same vertical position as that it lands at, right? The ground. It launches on the ground and lands on the ground. So it goes up in the air, gets to its highest point right here, and then comes back down. Okay, so the graph of its vertical position versus time looks exactly the same as the drawing there does. Okay, so now let's do the horizontal position. Now remember, the slope of position versus time is velocity. That means that the slope of the vertical position versus time is the vertical velocity, and the slope of the horizontal position versus time is the horizontal velocity. All right, so well, we know that the horizontal velocity of that object was constant. So guess what the slope of this guy should be? Constant. So the the horizontal position versus time graph is a straight line, just going like that, right? Because if you think about it, if this is 0, and remember, I think that was 83 meters or 87 meters or something like that the thing landed. So whatever it was, so it's 87 meters here. Then it's going to go start at 0 and just go steadily away horizontally till it hits the ground again, right? So that's how that graph should look. You should be hopefully pausing this and practicing on your own. Now what about the vertical velocity? This one's an interesting one. We know that it starts off, we give it a large vertical velocity up in the air. So it's actually going to start, you know, I need to do this better. Let me erase this real quick. I need to have my quadrant 1 and quadrant 4 in there. Draw like this. Okay. Alright, and the reason I'm doing this is because I'm going to have negative vertical velocity at some point, right? So I start off pretty high in my vertical velocity, but I slowly, now again, I'm going to reiterate this. The slope of a velocity time graph is acceleration. Therefore, the slope of a vertical velocity time graph is the vertical acceleration, which is -10, the acceleration due to gravity. So that means the slope of this line should be -10, so it just goes like this. That's it, right? And this point here corresponds to this point here, the spot where we stop for an instant and then come back down to the ground. Notice I have positive velocity all up here. This whole time, positive velocity, okay? And then on this side, I have negative velocity. That's when I turn around and start falling back down the ground, okay? And again, I'm gonna reiterate that the area under the curve of a velocity time graph is displacement. Therefore, the area under the curve of a vertical velocity versus time graph is the vertical displacement. Well, shouldn't the vertical displacement be 0? Since I launched from my vertical position, go up in the air and come back down to the same vertical position. Again, I know I'm further along the ground that way to the right, right? along the ground horizontally. But if I just think about vertical only, I go up and then I come back down, right? So it's the same spot. So if you add up this vertical displacement here and this vertical displacement here, guess what your answer should be? It should be 0. These little triangles we're making should be the same, right? All right, now let's talk about horizontal velocity. Well, the horizontal acceleration was 0. So the slope of my horizontal velocity time graph should be 0, and it is just flat like that, right? It's a constant. I think it was 26, wasn't it? It was 26 or 27, 28, something like that. I forget. I think it was 26 meters per second, constant horizontally. So there you go. Now for any projectile motion, it's pretty much going to look like this for all of them, right? More or less. But I want you to practice. So think about. Go ahead and draw something that is moving in 2 dimensions, right? Try a ball on a ramp, okay? And it rolls down the ramp. So it's moving horizontally this way, but it's also moving vertically down that way. So just see if you can draw the graphs for it, okay? See if you can get it. Just practice makes perfect. So just make up a problem. Think about kicking a ball in the air or throwing a ball down. Maybe you're on the roof and you throw a ball down at someone at an angle. Make up a situation and then draw its graphs. I want these 4 graphs. Position for vertical and horizontal position, and then velocity, vertical and horizontal velocity, right? Practice makes perfect, guys. Sorry. I can do these 100 times, but unless you're doing them and practicing them, then it's never going to sink in. So I want you to practice, practice, practice. So go forth, my minions, and do likewise. All right. Next slide, we're going to dive into some challenging word problems. So buckle up. All right, gang, we're actually going to start off with a graph/word problem here. I want to see if y'all can handle this, okay? I want to see if you got the right stuff or not. So here we go. We got a rocket ship blasting off. I got the graph of its vertical upward velocity, okay, on the graph here, for velocity versus time. I want to know 3 things. How high does the rocket get? At what time t does the rocket engine shut off? And then at what time t does the rocket begin to fall back down to the earth? All right, so I want you to pause the video right now. Pause it, and then solve for these things. See what you get. All right. Okay, you've unpaused the video. You're back, and you have your answers. Let's see how you did. Okay. How high does the rocket get? Hopefully you remembered that the area under the freaking curve is displacement. Now, once this rocket starts to fall back down towards the earth, right? It's going up. It's blasting off. Rockets are firing. Rockets firing. Then it's shut off. Oh, it starts to lose upward velocity, starts to slow down, and then it falls back down to the earth. Crashes, probably blows up in a million pieces. But how high did it get? Well, this is its upward velocity. So as long as we have a graph of this beginning part here, we got a graph of this, which we do, its velocity. We can find out its total upward displacement. So if we take the area under this curve of this whole big boy here, I got a triangle here, yellow. Oh wow, I really cannot draw. I am so not a good drawer. All right, you get the idea. That triangle right there. Okay, I'm actually gonna. I can't see what number that is. I'm gonna erase for a second. Okay, so right here to right there, make that triangle. Those 3 points. All right, and then we're gonna make a triangle in a different color. Let's go pink from there to there to there. Make that triangle. If we get the area under the curve, we're going to find its upward displacement. So what did you get? Well, this triangle is from 1, 2, 3. So this is 3 up. What's that? Looks like 120. So this is 3 times 120, and that's 360. Divided by 2 is 360 over 2. Can I do it in my head? God, I'm bad at math. 180. I knew that. All right, it's 180 in there. And the second much larger triangle, let's see, that's going to be 12 seconds on this side. And then we got, this is also 120 up there. So this is 12 times 120 divided by 2. Whoa, 12 times 120 divided by 2 is 720. So this area is 720. We add them up. That's 180. And we get 900. So the answer to this was 900 meters, right? So even though the slope here was going down, that doesn't mean that the rocket was falling back down to Earth. It was still going up in the air. I still had positive upward velocity. It was still going up. It just was slowing down, or I wasn't speeding up as fast anymore, I should say, right? It was losing its upward velocity. All right. So now, what about how high? Or sorry, not how high. We did that one. At what time t does the rocket's engine shut off? Ooh, now this is really just kind of there's no math to do here. We just got to think about it. It's t equals 0, 1, 2, yeah, 3. All right, it's right here. It's this point right here. It's t equals 3. The answer is t equals 3. How do we know it's t equals 3? Well, what is happening the moment the rocket's shut off? What's going to happen to that rocket? Gravity is going to go into free fall, right? Gravity is going to grab that sucker, that rocket, and it's going to yank it back down. Right? It's going to pull it down with all its might and fury. And so it's no longer going to have positive acceleration. It's going to have a negative acceleration. And negative acceleration should be -10, right? Because that's what the acceleration due to gravity on Earth is. So this is the point where our acceleration changes from positive something to a -10, right there. So that's when the rockets must have shut off. At what time t does the rocket begin to fall back to the Earth? Well, it's right here. It is t equals 15. You might say, "Oh, mister, you said its rocket shut off at t equals 3. Yeah, its rocket shut off. That doesn't mean it immediately falls back down, right? Doesn't it have a lot of upward velocity already? It's got to lose that upward velocity before it can actually turn around and then start falling back towards 0. So the rocket shut off at t equals 3 seconds. The rocket shut off, but then gravity grabs it, starts pulling it back down, but it doesn't immediately just turn around on a dime, right? It has a lot of upward velocity. It's got to lose that upward velocity before it starts to turn around, and that's when it turns around. It equals 15 seconds. So hopefully you were right. Maybe you got a couple of those right. Let me know how you did in class, or you can always ask about in the forums or whatever. But let's move on to the next problem. Alrighty, let's do the next one. We got a ball stone with an initial speed of 20 meters per second at an angle of 60 degrees to the ground. If air resistance is negligible, which, again, it always is, they like to say that, though, just to remind you, what is the ball's speed at the instant it reaches its maximum height from the ground? Ooh, okay. I like to draw a picture. Pictures are good. You should draw a picture, too. It'll help. All right, we're going to draw as a ball, launching it at 60 degrees from the ground. What does that mean? Well, there's the ground, right? Ground's horizontal, so 60 degrees from that, so that angle there is 60 degrees. Its initial speed is 20, so that means my total speed is 20, right? Not its vertical component or its horizontal component. They're giving you the total speed of the ball, right? We have to find its components. We must find Vx and we must find Vy naught. We must do it. It is our duty. All right. Well, I know the cosine of 60 is a half, so I know that my horizontal velocity is 10 meters per second, and if you're wondering, oh, how'd you do that? It's SOHCAHTOA, right? So it's SOHCAHTOA. And I know that this, the horizontal velocity component is adjacent to the angle, so I use cosine of 60 equals, adjacent side is the Vx over the hypotenuse, which is 20. Cosine of 60 is a half. At least I'm like 99% sure, but I'll do it anyway just to make sure. Yep, I was right. So it's a half times 20 equals Vx. I'm getting a little sloppy. All right, half of 20 is 10, so that's how I knew that, right? And then what about the Vy? Well, the sine of 60 is 0.87. So that means my sine of 60 is Vy naught over 20. Again, I'm using sine here, right? So the sine of the angle equals opposite over hypotenuse. Again, the Vy component is the opposite side of the triangle, so that's why I put in the Vy there. Sine of 60 is 0.87, so it's 0.87 times 20 equals Vy naught, and that's going to be 17.3. So Vy naught equals 17.3. Okay. So that's 70.3 meters per second. All right. We're on our way. Okay, hopefully you are getting better at finding those components. It is crucial. Okay. The problem wants to know, so let's write this stuff down. We have our Vx. It is 10. We have our Vy naught. It is 17.3. We know the acceleration due to gravity in the vertical direction is -10. And there is no acceleration in the horizontal direction. And what else do we know? That's about it right now. Okay. What is the ball's speed at the instant it reaches its maximum height from the ground? All right. Well, this is actually kind of a trick question. Have you caught on yet? Let me draw a picture here. Maybe it'll trigger your brain. But I want to make sure you got those components down. We don't know what the maximum height is, do we? If you drew a picture, it's right here, right? But we do know what its components are there, right? It's got a horizontal component. Does that change? No, it's still 10 right the whole time, right? Does it have a vertical component? No vertical velocity at the peak, right? At the spot where it has its maximum height. It doesn't have any vertical velocity there at that instant. So when it asks for speed, it means total combined resultant vector of the velocity. It wants you to add up the horizontal and the vertical to find the total speed. That's what they mean when they say speed, okay? Well, we don't have a vertical component of velocity at the peak at its highest point. We only have a horizontal component. So guess what the answer is? It's just 10. The speed at the highest point is 10 meters a second because the only velocity it has is horizontal, and the horizontal component is 10, so that's all we got. We don't have to worry about the vertical component there, okay? Now, just for fun, because it is fun, it's fun, we're going to find how high this ball got. How high did this ball get? So, in order to do that, we are going to do x, delta x, in the y direction, right, the height. So, remember, x stands for position, the subscript y is for the vertical plane. How high vertical position, v naught t vy plus 1/2 a t squared. I want to know how high this thing got. So I'm going to solve for my delta x, y. I know my initial vertical velocity was 17.3. I don't know what t is. I know y is -10. I don't know t equals delta x. I have two things I don't know. I don't know t or delta x. That's a problem. Oh, but I remember now. I have another equation. V equals v naught plus at. Oh, I got that guy. Well, don't I? This is vertical, right? Vertical, little y is here for vertical. Don't I know that my vertical velocity here is 0? Oh, I sure do. So that's there. My initial vertical velocity was 17.3, and I'm going to do minus 10 times t because acceleration is down, negative, right? So I'm going to add the 10t to the side, so I'm going to get 10t equals 17.3. I'm going to solve for t, divide by 10 both sides, I get t equals 1.73 seconds. So I know now I'm going to plug in the 1.73, this guy, meow, into that t, and into that t, right? Same t, right? Because that's how long it took to get to that spot. Because the only spot on the projectile motion where my vertical velocity is 0 is the very high, the tallest point, or the peak, or whatever you want to call it. So that's why I can plug it in there. So I'm going to plug it in. Delta x subscript y equals 17.3 times 1.73 plus 1/2 times a -10 times a 1.73 squared. I plug in the math, beedly doodly do. Let's do it real quick. 1.73 squared. How fast can I do it? Times a -10. Fat fingering everything. Alright, times 1/2. Okay, that's -15 essentially. It's like I got -14.96, but it's called -15. And then 17.3 times 1.73 is basically 30. So again, I got 29.9, whatever, round it up. So it looks like my final vertical position is 30 minus 15, which is 15 meters. So there you go, right? We got 15 meters. Did you get 15 meters? Did you get it? Okay, hope so. Or if not, you know what to do. All right, let's go to the next problem. One more. I think I got one more. How many more did I got? I got one. Yeah, one more problem. Let's do it. All right, guys. This is an old problem from, I think, one of the AP exams from like 20 years ago. But it's a fun one. It's a doozy. They giving you the values of sine, cosine, and tangent of 37 degrees. Just giving it to you. They do that sometimes because, they're such sweethearts. They're not really sweethearts. But anyway, let's do this problem. So we're going to ignore part A here. So let's read it just so we are on the same page. We got a ball. It's got a mass of 1/2 kilogram. It's at rest initially. It's kicked directly toward a fence from a point 32 meters away as shown. So you see horizontal displacement of 32 meters from the fence. The velocity of the ball is, as it leaves the kicker's foot is 20 meters per second at an angle of 37 degrees above the horizontal. All right. The top of the fence is 2.5 meters high. The kicker's foot is in contact with the ball for 0.05 seconds. The ball hits nothing while in flight, and air resistance is negligible. And part A asks about the magnitude of the average net force. We're not going to worry about that. It has to do with impulse and stuff like that. And we'll do that later. Let's focus on B, C, and D. Part B, determine the time it takes for the ball to reach the plane of the fence. So if you imagine that the fence kind of like extended up in the air, kind of up this way, this whole thing here is the plane of the fence, right? So if the ball goes over the fence, then it won't hit the fence, but it'll hit the plane of the fence, right? You kind of extend it up, and that's what they're trying to say. All right, so let's do it. This is going to be so much fun, you guys. I hope you all are excited. I'm so excited. God, I'm so excited. All right. What we got? Okay, what do we know? All right, we know that it's, let's see, we know A, acceleration in the y direction is, of course, -10. There is no acceleration in the horizontal direction. We can quickly find out the components. That's always our first move. What's the horizontal component? Vx. What is the vertical component? The y initial. And since it gives us the values of 37 degrees, it's kind of easy. We know that for SOHCAHTOA, Vy is going to be 20 times 0.6, so we use sine for the vertical component. So it's 0.6 times 20, so it's just 12. And then for Vx, and they're rounding this stuff too, if you're wondering. It's not exactly 0.6, but they're rounding it. Yeah, and then we got cosine of 20, 0.8 times 20 to get the horizontal component. 8 times 20, because we use cosine to find, this is 16, cosine to find the horizontal component. All right, so we know that this thing is going to go 32 meters. Okay, so the plane of the fence is 32 meters away. So right down the rest we know. We know Vx equals 16. We know Vy naught equals 12. All right. Well, I want you to pause the video and try to work this out on your own. It's a little tricky one, all right? It's challenging, but pause it now. Do the work. Okay, you're back. You tried it. Whatever. All right. Here's how you do it. We know the plane of the fence is 32 meters away horizontally. Well, how long would it take to get 32 meters? This is one of those rare times we're actually going to use the horizontal velocity to find the time. How long does it take to get there? Whether we don't care how high up the ball goes necessarily. We just want to know how long it takes to get to the plane of the fence. Well, the plane of the fence is horizontal. We gotta go to the right to get to the plane of the fence, right? So we're going to use a horizontal velocity to figure that out. We know it's 32 meters away, and we know that our horizontal velocity is 16, so we're going to solve for t. So we divide by 16 both sides, and we get t equals 32 over 16, which is 2. And even though I know it's 2 in my head, I still got to punch it in. I'm just like compelled to punch in the calculator. 2 seconds. All right, so the answer to part B is 2 seconds. Will the ball hit the fence? If so, how far below the top of the fence will it hit? If not, how far above the top of the fence will it pass? All right, well, the fence is 200 meters high. So if we find the vertical position of the ball after 2 seconds, we will know, right, whether or not it's below 2.5 meters, which is the height of the fence, or it was above 2.5 meters. So let's do it, you guys. Okay, delta x in the y plane is equal to initial velocity y times t plus 1/2 a t squared, you guys. All right, this is the equation I want to use because it's going to tell me what my change in position is after 2 seconds, right, with a constant acceleration, with my initial velocity being a positive 12, right? This is the equation I want. So let's do it. Delta x. And again, x for position, but we put a little y down there to remind ourselves, oh yeah, we're talking about the vertical plane here, vertical position. My initial vertical velocity was 12. what do I use for t? I'm going to use 2, right? Because that's how long it takes to get to the plane of the fence. So when the ball gets to the plane of the fence, am I going to be below the plane, or below the fence, I mean, or am I going to be above the plane? That's the question, right? So I'm going to use a 2 there, plus 1/2 times a negative 10 times 4, because that's 2 squared, right? All right, so let's solve the math here. 12 times 2 is 24, minus, let's see, 1/2 of 10 is 5, times 4 is 20. So, yeah, 20, right? So delta x y is going to be 4. So it looks like I'm going to clear that sucker. I am going to clear the fence. Hallelujah. All right, so wants to know, so will the ball hit the fence? No, it will not hit the fence. If not, how far above the top of the fence will it pass? Well, the fence is 2.5 meters high, and I'm going to be at a vertical position of 4 meters, so I subtract the 2, I get 1.5. So I'm going to clear that fence by 1.5 meters, right, above the top of the fence. With me? Got it? All right. If not, it's okay. You got time to ask questions in class or outside of class. All right. Let's do part D. Have I got room for part D? Let's do what's part D. On the axes below. Oh, I had graphs and I think I cut it off. Okay, axes below. Sketch the horizontal and vertical components of the velocity of the ball as functions of time until the ball reaches the plane of the fence. All right. So I'll sketch. Let me erase a little bit of this so I get room. I'm gonna sketch them right here. So once there was horizontal and vertical components. Okay, so we got horizontal velocity versus time, and then vertical velocity versus time. So the problem had like a graph for you to draw on, but we'll sketch it here. So again, guys, this we did this already, right? We practiced this before. The horizontal velocity does not change because there is no force acting on the object in the horizontal direction. So the horizontal velocity is constant. It just goes at 16 the whole time. All right, so it's just a straight flat line. Boom. Okay, I can't draw flat lines, but you know the drill. It's flat line, right? Horizontal line. The vertical velocity starts off at 12. This should be 12 here. You should label that here. This is 16, right? And then it's going to go. The acceleration is -10 the entire time because that's the acceleration due to gravity. So the slope should be -10 the entire time, like this. Right now, it hits the plane of the fence at 2 seconds. So we should only go to 2 seconds on our graph, right? And they will ding you on this on the AP exam. If they say to plot the graph until a certain time t, and you go past or not, or stop short of that time t, they'll ding you. Man, they'll ding you. They'll ding you like crazy. So don't stop short or don't go too long. Right at 2 seconds. So I should also have marked that the graph of my vertical velocity crosses the x-axis at 1 second, right? Because actually, it's not gonna be at 1, is it? Oh darn. Okay. Oh, okay. So why is it gonna be at 1? I was assuming that the ball hits the ground at 2 seconds, so I took half of that. But the ball is actually going to be in the air for a total time longer than 2 seconds. So where does the graph cross that x-axis? At what point times t do I have 0 vertical velocity? To find that, I'm going to do this equation here again, right? Plus at. All right, now my final velocity, I'm going to say that my final velocity for that variable there is the point at which I have no vertical velocity. That's what I'm defining it as. So that's 0. My initial vertical velocity was 12 minus 10 times t, right? I want to know exactly what time. The AP graders are mean, grouchy old people, and they hate young, bright students like you, so they're going to try to take every advantage they can. If you don't have this graph crossing the x-axis at just the right spot, they're probably going to ding you. So how do we know when to cross it? Well, at what point times t does our object have 0 vertical velocity, right? So we're going to solve this equation. So we get 10t over here equals 12. We solve for t equals 1.2, right? We just divide by 10. So this right here is 1.2 seconds. And then we stop the graph at 2 seconds because that's when the ball hits the plane of the fence, and that's when it said to stop the graph. There we go. We got it, okay? Hope that made sense. Hope you're good. Hope you're happy. You're all happy this video is over probably, but hope you probably learned something. I sure hope so. You probably have lots of questions. I would if I were you. Probably have lots of questions. So ask questions in the discussions forum on Schoology, or you can always message me on Remind. But ask them there and see maybe your students want to reply and have a discussion on there. All right, guys. Hope you enjoyed the video. Message me anytime. Email me day or night. I have no life. You are my life. I'll see you in class. Enjoy the rest of your weekend. Bye.